Well, hello there. This is Craig Hane. Students call me Dr. Dell. Good friend of mine, David Chung, pointed out to me that some years ago, there was this supposedly the most intelligent, highest IQ woman in the world, Marilyn Vos Savant, had told a story that mathematicians thought was wrong. It was called the Monty Hall problem. And many mathematicians were wrong about it, and they condemned her and all that. It turned out they did experiments to prove that she was right, so on and so forth. And he told me about it. And so I thought about it. And in about 30 minutes, I figured out Marilyn was right. I can't even imagine how the mathematicians were wrong. And so what I want to do on this video, I'm going to discuss the problem. The Monty Hall problem is called, and how I would explain it to anyone, let's say an eighth grader or anyone young person. And here's the problem. I'm going to do all this. You can take a piece of paper and write something down if you want to. Here's the Monty Hall problem. You have three doors, and you're the player. And behind one of the doors is a prize, and behind the other two doors is no prize. So the question is, as a player, we're going to play by two different sets of rules. Rule number one, you open up a door. You pick one of the three doors. And what is the probability that you will win the prize? And since there's three doors and one prize and three doors, what do you think is the probability? If you just randomly open up a door, you'll win the prize. And if you said 1 in 3, 1/3, that is correct. That's the probability. Now, here's the way we're going to play the game, the Monty Hall game. Two different ways. Number one, Monty Hall is like God. He knows which door the ball is behind. And so when you pick a door, obviously, out of the other two doors, at least one of them will be empty. And Monty Hall will open one of them and show you an empty door. And then you open your door and see if you won the prize. And what's the probability you will have won the prize under that set of rules? And if you said 1/3, you'd be right. That's the same option. And the way you can do that, now let's do the experiment and prove it. Let's say that there's the three doors and the prize is behind door number one. Monty knows that. You don't know it, Monty knows it. And you go to choose one of the three doors. Now you got three choices, 1, 2, or 3. And if you choose 1, you'll win the prize. If you choose 2, you'll lose the prize. If you choose 3, you'll lose the prize. Right? So you got 1/3 chance of winning. Now, the rule number, we're going to play the game by number one is you're going to pick one of the doors. Monty Hall is going to open up. He knows where the ball is. He's going to open up one of the doors that doesn't have a ball behind it, show it to you, and then you don't do anything. You just open your door. Did you win or not? Okay, so let's do that. Let's play that game. Now, God knows, Monty Hall knows it's behind one, but you don't. And we're going to play the game 3 times. So time number one, you don't know which one is behind, but Monty does. So time number one, you pick door number 1. Your probability, of course, of winning is 1/3. Monty opens up one of the doors that doesn't have a ball behind it, shows it to you, but you don't do anything, and you open up your door. Well, you won. Now, let's say the second time you play the game, you pick door number 2. Again, we know, Monty Hall knows it's behind one, but you don't. You pick door number 2. And Monty Hall opens up a door that does not have one behind it. You don't do anything. You open your door. Did you win the ball? No. This was door 2, so you lost. Let's play the game a third time. Third time, you pick door number 3. Once again, God knows, Monty Hall knows it's behind one. You don't. You pick the third door. And Monty Hall opens up a door that does not have a ball behind it, and you don't do anything, and you open your door. Did you win? No. So you played the game 3 times, and you won once out of 3. So your probability of winning was 1/3. Now we're going to change the rule. And this is where Marilyn Savant got, first of all, herself kind of into trouble, but really in mathematician trouble. Here's the new rule. You're going to play by. You're going to pick a door. And then Monty Hall is going to open a door that doesn't have the prize behind it. And then you are going to select the other door that you didn't pick. In other words, you pick a door, Monty Hall opens up a door, doesn't have the ball behind it. That leaves a different door, and you pick it. You switch doors. And the question is, now what's your probability that you're going to win the prize? And Marilyn said, well, let's do the game and see. We'll see what Marilyn said. So let's do it. Now, same game of before. Now, when Monty opens up a door that doesn't have a ball behind it, you're going to change doors just automatically. Nothing to think about. You're just going to do it. It's the rule of the new game. So now we'll go back, start over again, 3 doors. The ball's behind door 1. You don't know that. God knows it. Monty Hall knows it. Okay, now let's play the game. You pick door 1. Monty Hall opens up a door that doesn't have a prize behind it, and you automatically switch to the other door. Now what happened? Well, you switch to the door that he didn't open, doesn't have a ball behind it. So what happened? You lost. This particular time you lost because you opened up the door that didn't have the ball behind it. That's a loss. Now we're going to play the game again. This time you pick door number 2. Monty Hall opens up a door that does not have a prize behind it, and you automatically switch. Well, he couldn't have opened up door 1 because he's got the ball behind it. So he had to open up door 3. You don't know that, but he did. Not Monty Hall knew it. And so you switch, and now what happened? You win the ball. Play the game a third time. Again, you pick door number 3. Monty Hall opens up the door, doesn't have a ball behind it, and you automatically switch. Well, of course, now, since you picked door 3, he had to open up 2 because he knows. And you switch automatically. And again, you win the ball. So what happened? You played the game with the rules I just gave you 3 times. The first time, when you switched doors, you didn't win the prize. But the second time you won the prize, the third time you won the prize. So if you play by that rule, what's the probability you're going to win the prize if you play by that set of rules? Namely, pick a door, Monty Hall shows you one that's empty, you switch doors. And the answer is you won twice out of 3 times. So the answer to the probability is 2/3. Now, just think about that. And I believe that would convince anybody, just from common sense reasoning, that if you play by this new set of rules, you'll win 2/3 of the time. If you play by the original set of rules where you didn't switch doors, you only win 1/3 of the time. And that's what Marilyn Savant pointed out. Now, I guess she didn't give an argument to convince people. So then I guess what David tells me, a lot of people then experimented. They experimented. And when they experimented and used that second set of rules, when they use the first set of rules and let's say they do it 100 times, they win about 1/3 of the time. When they play by that second set of rules and they do it, say 100 times, they win about 2/3 of the time. So experimentally, the answer is 2/3. Well, I just gave you the logical reason why it is. Whenever you play any game by a specific set of rules, what's the outcome going to be? Well, then you have to analyze what would the outcome be. In this case, by switching to the doors, once Monty Hall showed you a door that didn't have it behind it, you won twice and lost once, so you won 2/3 times. So that's my story. It took me about 30 minutes to figure that out after David told me the problem. And I don't think it's a very deep problem. But when you study probability, it can be very counterintuitive. And so you really have to go through and do a basic analysis. This is, I think, a particularly easy problem. And there's other things in probability that are very counterintuitive, and you can easily not understand it. When you get into things like Bayes' theorem and things like that, you can get into situations where it's counterintuitive. Probability is a very difficult subject. And by the way, as I told David, when you get into probability involving infinite sets, it becomes even less intuitive, and you can go really wrong when you're dealing with infinite sets. An example I gave David was, if you take all the real numbers between 0 and 1, there's 2 kinds. There's rational numbers that can be expressed as fractions, and there's irrational numbers that cannot be expressed as fractions. A real number is any, between 0 and 1 is any decimal expansion. 0.345, ... Infinite decimal expansion. Those are real numbers by definition. And we have an axiomatic system to prove all that axiomatically. Everything I'm going to tell you now is absolutely provable. Now, You take all the numbers between 0 and 1. In between any two rational numbers will be an irrational number. In fact, there'll be an infinite number of them. Between any two irrational numbers will be a rational number. So they're clearly completely interspersed in a dense way. Rationals and irrationals are interspersed in the real number, both of them in a very dense way. Meaning between any two rationals, there's a bunch of irrationals. Between any two irrationals, a bunch of rationals. Okay, now the question is, if you reach in at random and grab a real number at random that's in between 0 and 1, what is the probability that that'll be a rational number? And what is the probability it'll be an irrational number? By the way, those two probabilities, since those are the only two choices, have to add up to 1. Always. So what's the probability it'll be a rational number? And a lot of people that don't understand theoretical math would say, well, 1/2. Because, you got rational, got irrationals, or they're all dense. And the answer, that's the wrong answer. The answer is 0. And the probability you'll get an irrational number is 1. And that's all based on what is called measure theory, Hausdorff measure theory. And any probability theoretical mathematician knows probability will tell you that's the answer. It's counterintuitive. And if you're not a theoretical mathematician, that you think that's crazy. Because theoretical math, from an intuitive viewpoint, is very often crazy, believe me. And you find that out when you get into science. When you get into quantum theory and relativity theory and modern science, there's so many things that go along with the math models that are counterintuitive that even today, scientists are puzzled by it. Quantum theory predicts something that, based on the model for quantum theory, is provable, that Einstein said is crazy, and it's spooky action at distance, and it's wrong. But even to this day, quantum theory proves it. Einstein says it contradicts his general relativity theory, or his special relativity theory, actually. It contradicts. And in a certain sense, it does. And what it really does, now I'm going way beyond Marilyn Vos Savant, it really leads us to a new physics theory that goes beyond either quantum theory or relativity theory. By the way, those two contradict each other in certain circumstances. We have a new theory that goes beyond that most people don't even know about. Dr. William Tiller has come up with the best model I know of. There's some other models out there too, but that's the one I think is the best one I know. And it's very counterintuitive. And what it really boils down to is Einstein thought that the only thing that existed in our universe or in the world or in reality was physical things, and none of which could travel faster than the speed of light. In fact, if they had any rest mass, they couldn't even go the speed of light. A photon doesn't have any rest mass, although it does have mass and energy, and it travels at the speed of light. Okay. Well, it turns out, no, there is a lot of stuff that goes faster than the speed of light that our physicists don't recognize because they haven't discovered it yet. Although William Tiller has proven it exists with a set of experiments, and he also has a math model for it that very few people understand, because the math model for the non-physical universe that we all live in, we're immersed in it. The math model for that is similar but different from the math model for the physical universe, although it's kind of similar. You have Maxwell type equations for his math model. So that's another story altogether. But life is complicated. Life is counterintuitive. And even the most genius men in the world can make a horrible mistake. Back in the time of Isaac Newton, up until the time of the 16th century, the 1600s, the 17th century, everybody thought that the Earth was, I guess everybody thought the Earth was the center of the universe. We have the Ptolemaic model that described the movement of not only the stars, which are fixed, but the planets. Along comes Copernicus and says, no, I have a new model. The Earth is the center. I mean, the sun is the center, and the Earth goes around it, and all the other planets go around it. It's a Copernican model. He was so afraid to tell people about it, he didn't release it till he was on his deathbed. And people thought he was crazy. And then Kepler took a lot of data that he and Tycho Brahe had collected and showed that if you considered the sun the center, the planets went in an elliptical order around the sun. And Isaac Newton came along. Now he did that from experimental data. He had no idea why. And he came up with what are called Kepler's laws based on experimental data. Newton came along and said, well, wait a minute. He came up with a theory of gravity. And with the theory of gravity and with calculus, he had to have calculus, which he was one of the inventors of it. He was able then with that math model to show that the planets did, in fact, orbit the sun in an elliptical model. And then Galileo, a little bit before Newton, had the telescope and they saw the moons around Jupiter. And so over a period of less than a century, the smartest men in the world went from believing the earth was the center of the universe to knowing that the sun was the center. And then it went on from there. And for a long time, they thought that we were in this Milky Way galaxy and that was the whole universe. And then in later centuries, we discovered, no, there's other galaxies and lots of other galaxies and so on and so forth. But even today, there's things we don't understand about cosmology and universe. There's something they call dark matter they don't understand. There's something called dark energy they don't understand. And they admit they don't understand it. The two greatest theories today, and by the way, Newtonian theory was replaced by Einstein's relativity theories. They're better than Newton's theories, and we have experimental evidence to prove it, no doubt about it. And Einstein's relativity theories, without them, we wouldn't have what's called GPS, for example, global positioning system. Quantum theory then came a little bit after that, and that's the reason we have really today everything we understand about chemistry and electronics and all that kind of thing is quantum theory. Quantum electrodynamics, and then for nuclei, quantum chromodynamics. Only one problem. Those two theories, our two great theories today, that our technologies that we have are based on, contradict each other in certain circumstances. Physicists don't know what to do about it. Tiller does. Tiller's kind of a new theory that shows how they're integrated. And I won't get into that on this video because it goes way deeper than that. But Tiller's written several books. You can go to his website. He's got all kinds of white papers on it. I might add the mathematics is pretty deep. It's not high school level mathematics. You've got to understand mathematics at a much deeper level than just high school math. So you go through my 6 tiers. I can't get through calculus and differential equations, but there's way more to go. And by the way, thanks to the tool Wolfram Alpha, it's much easier now to go way further. So that's a whole other story. And then you get into question today of artificial intelligence, and I'm going way beyond now. That's a big controversy today. And I won't get into that now in this video. I've gone far enough. I wanted to show you my analysis of the Monty Hall problem, how I would explain it to any bright 8th grader. And they might understand it quicker and easier than a Ph.D. mathematician, some of them anyway, that think they've got a different way of doing it. Okay, enough of that. This is Craig Hane. I just wanted to do that as a fun video. And so there it is. And I will maybe see you on some other videos. Bye-bye.